Awesome. Well, welcome everyone. My name is Shelby Arndt, and thank you for tuning in to the USGS Landslide Hazard Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with John Perkins and Jamie Kostelnik. For those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature along with your microphone and video. And we will wait till the end of the presentation to take questions. In the meantime, please do your best to make sure your microphone is muted when you are intending to speak. It is my pleasure to introduce Liam Toney today, who is a research geologist in the USGS Geologic Hazard Science Center out of Golden, Colorado. Liam received a bachelor's in physics at Pomona College before getting his PhD in geophysics at the University of Alaska Fairbanks. He was a Mendenhall postdoc before accepting a position as a research geologist earlier this year. Liam thinks about sound waves and seismic waves in his research, specifically to investigate non-earthquake geohazards like landslides, avalanches, and volcanic eruptions. And today he's going to talk about how he's used seismocacoustics to analyze an ice rock avalanche in Denali National Park. So with that, you can take it away, Liam.
Great. Well, thank you for the introduction, Shelby, and thank you to the organizers of the LHP seminar. It's always a highlight of the week to tune in on Wednesday afternoons. And I'm really excited to be giving this talk today. I gave one previous LHP seminar in 2020 when I was a Pathways intern, when this format of presentation was the only format available. In looking through my slides, I've realized I'm using at least one slide from that presentation 5 years ago. So I guess I'm saying the same thing 5 years later. Yeah, so I'll start with the main takeaway from this presentation. This presentation is going to be all about how superficial mass movements, landslides, avalanches, the like, disturb both the solid Earth and the atmosphere. And they produce seismic waves and acoustic waves. And for large and rapid events, those waves can travel for hundreds of kilometers. And in this talk, I want to emphasize how these two types of waves can give us a complementary view into the landslide, and how, in addition, these data types have very high temporal resolution, so we can make statements about temporal evolution of failure dynamics, and often seismic and acoustic data, at least in non-lab environments, are the only data we have from during a landslide. So they're really great data sets to use for landslide monitoring and characterization. In this talk, I'll spend a little bit of time talking about background of landslide monitoring using seismology and infrasound. And for infrasound, I will spend a bit more time giving some background just because it tends to be a newer technology for folks. I'll talk a little bit about Alaska's geophysical network just because the degree of station coverage we have in Alaska really contributed to how well we were able to characterize this Denali avalanche, which I'll talk about in the final part of this talk. So let's talk about landslide monitoring using seismology. I've got a few photos on the slide here. They're all from the USGS field exercise at the Slumgullion landslide in Colorado last summer. On the far left is a picture of a broadband seismometer. For reference, this is about the size of a coffee cup, but it costs significantly more than a coffee cup, turns out. In the middle here, we have Kate Allstat installing a seismometer as Elaine Collins looks by. And then on the far right is a picture of what one of these sensors looks like when it's buried in the ground. So landslides generate broadband seismic energy. And by broadband, I mean that the energy they create is across a wide range of frequencies. And the energy is in the form of waves. And so I've put just a visualization of what a wave can look like. On the far left, we have what we call low frequency energy, also called long period. These waves have large spatial wavelengths. And then As we move up the frequency spectrum to higher frequencies, we have high frequency, short period, and smaller spatial wavelengths. And I've put some of the basic wave relationships and variables up at the top right of the slide. And so we can think of the mechanism of seismic wave generation by landslides as this spectrum. Again, on the left, we have the long period seismic waves, and these are made by sort of bulk momentum transfer into the earth from the landslide. So as an example of this, consider this satellite image of a large rock avalanche in Alaska. It failed to the northwest and then impacts the side of this valley. And you can imagine there's a tremendous amount of force exerted on that side of the valley by this landslide as it deflects and then moves to the east-northeast. And so this is going to generate really strong long period energy. And then on the far right, the high frequencies, these are generated by processes that are happening rapidly and sort of smaller scale. And this is a schematic. This is actually from a river seismicity model, but it also applies for high frequency generation from landslides. You can see we have all these particles, and they're impacting one another, and they're impacting off the substrate, and that generates high frequency seismic energy. And just another way to picture this is, as we move more towards the long periods, this is more of the deterministic aspect of the dynamics. It's governed principally by topography and how the landslide is interacting with it. And then as we move to higher frequencies, it becomes more stochastic. We have these random particle impacts. So we can leverage this deterministic aspect of the long period seismic wave generation to understand the dynamics of failure from these landslides. And so for large and rapid landslides, when we consider long period seismic waves, we can simplify our conceptual model of failure to basically a rigid block failing down a slope. And so when we make a few assumptions, we can use these long period waves to invert or infer the time series of forces that the landslide exerts on the Earth as it travels down slope. And so while this does require assumptions, those assumptions are typically met by large and rapid landslides. So we can also locate large and rapid landslides using the long period seismic radiation that they produce. And so this slide, I'm showing an example of an algorithm developed by Ezgi Karasozin and Mike West at the Alaska Earthquake Center that's currently running on continuous seismic data in Alaska. And it's based on the idea that you have a bunch of seismic waves in long periods. Time is on the x-axis here, and distance from a source is increasing as we go down. And if we have a search grid, which is shown in yellow here, for each trial grid point of that grid, we can say, okay, if there was an event there, how would those waves line up as they move away from the source? And it turns out that at the true location, those waves will align and they will sum up constructively. And that can be used to identify the XY location and the time of failure of these landslides. So here are 3 examples from the Barry Arm region from this paper. And one of the things you get out of this, along with the X, Y, and the T, is the degree of agreement between the waveforms. And so you run this on real time in Windows, and then when you have this high stack coefficient or sum agreement between the waveforms, that can be used, that can be thresholded to generate detections and therefore generate a catalog of events producing long period seismic radiation. And I just wanted to highlight this algorithm because it's really cool, and it's helping us understand just how many large rapid landslides are occurring in Alaska that otherwise might go unnoticed for weeks or months until someone sees satellite imagery or a pilot flies overhead. So let's move on to talk a little bit about infrasound from landslides. And again, I'll talk a bit more broadly about the background of infrasound generation and propagation, just because it might be a newer technology for some. On this slide, I've got, again, some photos On the far left, I'm holding an infrasound sensor. It's basically just a microphone, a really nice microphone that's recording pressure differences over time. In the middle here, this is a photo from the Barry Arm landslide in the Prince William Sound of Alaska, and we're looking west across the fjord towards the area of active movement. And in the foreground, there's this black box. It's a pelican case that contains the sensor, and that box is right next to this pyramid-shaped metal dome. And these domes have a couple purposes, but they help to reduce wind noise. And importantly, in this area of Alaska, they help protect the sensor from curious bears. And on the far right, it's another picture of an infrasound installation. This one is on the Kenai Peninsula in Alaska, and it was installed to monitor the volcanoes that are across the Cook Inlet, such as Redoubt, Spur, and Iliamna. But this infrasound installation also records a lot of mass movements, such as rock avalanches and snow avalanches on those volcanoes. So what is infrasound? So we're all familiar with the acoustic spectrum, and that's audible sound. That's how I'm communicating with you guys right now. And that's defined as sound between 20 hertz and 20,000 hertz. But just like with light, sound is a spectrum, and so we have both infrasound and ultrasound. And those are defined as ultrasound is sound above the threshold of human hearing, above 20 kilohertz, and infrasound is below the threshold of human hearing. And it turns out that infrasound is generated by a lot of natural and anthropogenic sources. This schematic here on the bottom left just shows some of the many sources that can produce infrasound. And infrasound is kind of like seismic waves. It's related to, the frequency of infrasound is related to the size of the source. And so you have a larger volcanic eruption is going to produce a deeper tone relative to a smaller process, for example. And one kind of fun fact about infrasound is that elephants actually produce infrasound. And so this is a paper from a colleague that was using infrasound, just the same type of sensor that we can use to record landslides and volcanic eruptions. He was using it to record elephant vocalizations. So we communicate using audible sound, elephants use infrasound, and bats make ultrasound. But I'll be focusing mostly on infrasound today. And infrasound, kind of like with seismometers, we can be strategic about how we install infrasound and the configurations of sensors that we use. And there's two main styles of sensor configurations. On the left, I'm showing a network style. And so this is defined by your source being approximately as far from your sensors as your sensors are from one another. And this is fairly common for earthquake monitoring as well. So if you have an earthquake monitoring network, say across Southern California, it's a network style monitoring strategy. But there's another strategy called array monitoring. And this is where the source is quite far from the sensor. So this is not to scale. The source will be much farther away. And it produces sound waves. And those sound waves emanate from the source spherically, but in the limit that you're really far away, they look sort of like plane waves. So they look like these straight waves or straight wave fronts that we see here. And you have a strategically arranged collection of sensors, typically tens of meters to hundreds of meters apart from one another. And these waves will propagate across your array. And what you can do is measure the difference of arrival, time difference of arrival between the different sensors. And you can also measure how well the waveform recorded on one sensor agrees with the other ones. So basically, if it's a true source of sound, then the waveforms recorded on those elements will all look about the same. But if it's random noise, then the noise will look different. For example, wind noise will look different on each sensor. So with some processing, we can compute the back azimuth, which is just simply the direction the sound came from. And so this is a super powerful technique that we use very, very often in the infrasound world for characterizing sources and locating sources. So let's consider an example of this and what this processing actually looks like. So I have the same schematic on the left, and now on the right, I'm showing an example of processing from some data. And on the x-axis for all of these subplots is time. We're looking at, I guess, a 4-minute long window here. And from top to bottom, we have the pressure waveform recorded at one of these sensors. So this is just pressure fluctuation over time. The next panel is that agreement metric I'm talking about. So when we have a true signal, not just some random noise that's different on each sensor, we have true signal that looks similar on each element, then this value will be high. This is also encoded to the red color on the color bar for all panels. And the next panel is the apparent speed of the waves across the array. So to consider this, imagine you have an array that's on a flat plane and you have a sound wave propagating horizontally across it. That velocity will be the speed of sound. As it is here, you can see it's about 330 meters per second. However, if you have some elevated source, then there's an incidence angle, and this velocity will be higher. And the way to think about that is if you had a source that was directly above the array, then the sound waves from that source would hit each element of the array at exactly the same time, and this velocity would be infinite. So this velocity can be used to map to the incidence angle of the waves. And then the final panel here is what I discussed earlier. This is the direction that the sound came from. And you'll note that there are little dots here, and that's because each dot represents a time window. So we do this processing in overlapping time windows where we compare snippets of wiggles with one another. And this example is actually from the baryarm infrasound array. So earlier I showed a photo at this green dot looking to the left in the image west. And in this case, this processing has identified that there's a source of infrasound coming from across the fjord. And this is very likely a snow avalanche or rockfall, that similar activity. And in a place like Baryarm, this is really important because it's a very, very noisy place. Berry Glacier, this tidewater glacier here, calves extremely frequently. And so using the back azimuth and the incidence angle, it's one way we can identify different sources of infrasound waves and therefore different types of failures that are occurring. And this array is about 2 kilometers away from the active landslide. So to understand the source of seismic or infrasound waves, we need to understand how those waves are modified as they propagate through the atmosphere. This is similar to in seismology, where if you want to understand the source, you have to understand what happens to seismic waves as they travel through the Earth. And this is where I love talking about infrasound because it has so many direct analogies to our lived experiences with audible sound. And here are sort of 2 examples. And propagation is principally for infrasound controlled by 2 things. And the first is interactions with topography. So in the same way where if you're in a canyon and you give a shout and it reverberates, bounces off the canyon walls, the same thing happens for infrasound. And so infrasound will reflect off of surfaces, it'll diffract or bend around surfaces, and that can complicate your infrasound signal. And the wavelength of the infrasound determines what scale of object it's sensitive to. And so infrasound wavelengths can be hundreds of meters long, and therefore they don't really care about like a small boulder or a tree or something, but they see larger things such as mountain ranges. The other thing that infrasound is very sensitive to is atmospheric structure. And this is more important when we're looking at regional infrasound, so infrasound that's traveling more than 50 kilometers, say, in the atmosphere. And what happens basically is that infrasound travels up in the atmosphere, and atmospheric temperature and winds modify the sound speed. So as things get hotter in the atmosphere, the sound speed increases. And same with the winds. The winds can increase the effective sound speed depending on the direction of the winds. And when that sound speed gets larger than the sound speed at the surface of the Earth, your waves will bend back towards the Earth. They'll refract back down, and then they'll bounce when they hit the Earth's surface, and then they'll go up and they'll refract. And so this can create what we call atmospheric waveguides, or ducts, where infrasound can propagate super efficiently in the atmosphere. And that's what this schematic is showing, X and Y here, range and altitude, and it's showing these different layers in the atmosphere where the infrasound is really effectively propagating. So this can play to our favor, and we can record infrasound at great distances. One example is there was a recent science paper about a large landslide in a seiche in a fjord in Greenland, and they recorded infrasound from that event at 3,300 kilometers away in Russia. And this was due to favorable propagation conditions with these waveguides. However, it can work against us as well, because if the wind is blowing away from where your sensor is, it's kind of like when you're yelling and your buddy's upwind and they can't hear you because the wind is whipping your words away. We get a similar effect happening with infrasound. And another massive challenge with infrasound propagation is that, unlike in seismology, the medium of propagation is changing not only in space, but also in time. And this is the time scale of this is from minutes to hours, and can massively affect your detection capability. And we can get stuff like seasonal variations in detection capability, depending on where your source of interest is relative to where your array is. So that's a little bit of background on seismology and infrasound, and that will be important because those two technologies play a major role in the analysis I'll talk about with this Denali landslide. Now I want to talk briefly about Alaska's geophysical network. I like showing this schematic just because it demonstrates how large Alaska is. It just shows that even the bulk of mainland Alaska is considerably larger than Texas. Sorry, Texas. And if you factor in the Aleutian Islands, which do have, for example, highly active volcanoes and large earthquakes, you have a really large spatial extent of state to monitor. And as I've alluded to, Alaska is extremely geologically active. Here's a map of the seismicity in Alaska in 2023, and we have a ton of seismicity from the Aleutian subduction zone and crustal earthquakes. And so this requires a robust network of principally seismometers to monitor effectively. Likewise, for volcanoes, Alaska has over 50 historically active volcanoes. They're shown as these red triangles going out the Aleutian chain here. And some of these are in extremely remote areas. And sometimes we're able to get out there and install or service existing geophysical networks, but some of the monitoring capabilities is really relying on long-range propagation of, for example, infrasound waves to effectively monitor remotely. And so as a result of these geohazards, Alaska has, as I've mentioned, very robust earthquake monitoring networks and volcano monitoring networks. In addition to that, Alaska, like the lower 48, benefited from an NSF-supported program called the Transportable Array, which basically installed a ton of seismometers across the lower 48, and they moved over time, and then they moved up to Alaska. And this was principally to understand subsurface structure via seismic imaging. But the good news is that a lot of those stations that were installed in Alaska ended up being adopted by the regional monitoring networks and are now permanent. So as a result, Alaska has quite a robust seismic and acoustic network. This is a snapshot of what that station map looks like as of September 2024. And the brown squares are seismometers, and the blue circles are infrasound sensors. And I'll note that there's quite a few sort of co-located instruments. And that's because if you're going to put the effort in to take a helicopter out, put in a bunch of instrumentation with a digitizer to record the data, with batteries to power the equipment, and telemetry, cell modems, etc., satellite telemetry, it makes a lot of sense to get value added and install, say, an infrasound sensor as well. So there is just a huge amount of potential for using seismic and acoustic data to monitor events across Alaska. And the median station spacing here is about 60 kilometers, which is quite good. So that really sets the stage for the final portion of this talk, which is I'm really going to talk about this avalanche and explain how we used a multitude of technologies, not just infrasound and seismic, to respond to it rapidly and also characterize it in the weeks and months afterwards. I'd like to acknowledge my co-authors on this work who span 6 organizations and really highlight the sort of multi-agency and interdisciplinary nature of landslide monitoring. So at around 6 p.m. on September 13th in 2023, a seismic event was detected in the vicinity of the mountain Denali in Denali National Park and Preserve. And I put this in quotes because at the time, that's all we knew about this event. We had seismic waves, and it was indicated that it was some source that was close to Denali. But for non-earthquake sources, this is really often how it happens. First, you see that something has occurred, and then you have to understand, okay, what was it when it clearly isn't an earthquake? And this is just a map showing the shaded area is the boundary of Denali National Park and Preserve, and that black triangle is Denali. And so what happened after this detection occurred? This is a timeline illustrating various events that occurred in the 24 hours after the event. And it's color-coded by the institutions that were involved. So we have Denali National Park in blue, and then the Alaska Earthquake Center, which is housed at the University of Alaska Fairbanks in orange, and then the National Earthquake Information Center in green. And the NEIC are the folks that are upstairs on the 5th floor for those of us in golden, the USGS office there. And so what happened was there was an automatic detection of an event by NEIC operational earthquake monitoring systems. These are systems that are not designed to be catching landslide events. And then shortly thereafter, the code that I've mentioned previously that I highlighted that is landslide specific, that uses long period seismic waves, also detected an event. And about 30 minutes after the event occurred, it was still light out in Alaska at that time in September, and an air tour operator, a pilot that was in the vicinity, saw a dust cloud and took a photo. And within the first hour of this happening, it was determined that given the long period seismic location and the waves produced, it was likely a landslide that had occurred. And in the next morning, so we have a little bit of a broken axis here overnight. The next morning, the Earthquake Center contacted Denali National Park, and some refinement occurred of the locations. And this equipped Denali Park staff with enough information to justify doing an aerial recon flight in a fixed-wing aircraft. So that occurred later in the day. They got out there, they took some photos, and they returned. And then finally, staff at the University of Alaska Fairbanks completed some additional work characterizing the dynamics of the event, and then in addition, determining that there had been multiple events prior to the main failure. And much of what I'll talk about in the remainder of this talk sort of addresses some of the analyses we did here. And then there's additional analyses that we were able to perform with additional geospatial data, etc. So here is a map showing the various stations that are involved in the analyses used in this work. It's fairly small, so I'll skip over some of this stuff, but I just want to note this yellow to black color scale, the heat map there, that is the location code I've mentioned previously that's using the constructive sum of seismic waves. That's the final heat map location for this event. And the green polygon we see here is the intersection of the back azimuths from 4 infrasound arrays that are shown as green pentagons on the Kenai Peninsula, in Whittier, Alaska, at Barry Arm, and then up in Fairbanks. But let's zoom in on the inset here that shows the immediate vicinity around Denali. So the event occurred just off the north summit of Peters Dome, just over 10 kilometers northwest of the summit of Denali. And I want to draw your attention to these blue circles and stars. These are the locations output by the NEIC earthquake monitoring systems. And locations 1, 2, and 3 are automated locations. And then the ones in cyan for 5, 6, 7, and 8 are when a manual analyst came in later after the 24-hour period to refine these locations. But I just want to point out that the automated earthquake-focused system actually located this event within 5 kilometers of the true location. The star here in red that's labeled 2, this is the long period location. And then I'm showing here in a brown polygon the final outline of the deposit from the event. So this event produced really energetic seismic waves and acoustic waves. And so it was widely detected, including being detected, as I've mentioned, by this real-time long period system. So this is a screenshot of an email that was sent out just 4 or so minutes, or 4 to 6 minutes after the main failure, alerting the authors of this tool, as you can see in the email address thread there, to a detection. And interestingly, this tool was initially only set up to be monitoring the Barry Arm region of Alaska because it was designed to rapidly detect a potentially tsunamigenic landslide in that area. And so the search grid for this tool did not encompass Denali. So what you see here in this heat map is that there's sort of some lobes of energy, but it's kind of off the grid. And so that was one challenge, is that the tool wasn't actually optimized for the location of Denali. However, it was still able to detect the event. Here is what we call a seismic record section of the high-frequency seismic waves produced by the avalanche. So on the x-axis is time measured from the start of the avalanche, and then the y-axis is distance away from the avalanche. And we can see this very impressive presence of both a P wave and an S wave arrival from this event, as well as 2 events preceding the main failure that are sort of vaguely, they're faint, but they're there, that are seen also moving out across the network. And then we can also look at the long period seismic energy. So this is the same right-hand slice of this panel, but just filtered to only look at the long periods. And this is just a remarkable record of energy moving out to well beyond 400 kilometers from the source. And so when I look at these long period waveforms, it's not surprising that a tool such as the tool by Karasozen and West was able to detect this event so well. What I did find really interesting when I reapproached the way that this detection was made by the automated earthquake systems is the number of automated waveform picks made on the high frequency data. So these colored circles, each colored circle represents an algorithm noting that energy is present in the data stream for a particular station. And so these are called triggering algorithms, and this is one of the first steps in automated earthquake monitoring, is just detecting that there's some type of seismic energy. And really notably, these are tuned to detect earthquake seismic signals. Yet, we see that for almost all of the stations, the P wave arrival has been automatically picked. And interestingly, it's been labeled by a seismic phase classifier as being an S wave rather than a P wave. So that's beyond the scope of what we're going to talk about today, but it's an interesting ramification for how earthquake systems see the seismic signals produced by mass movements, by non-earthquake sources. So here are some photos of the event. The top left panel was acquired actually not on 14 September, but this is the photo from the tourist flight scene. North is to the right in this image, and you can see in the center of the image this sort of low-lying dust cloud that's hugging the flank near Peters Dome. The other images were taken during the aerial recon I mentioned by park staff the following day. And in panel B here, just to orient you, we're looking basically to the south. The flank of Denali, which is absolutely aerial here, is seen towering over Peters Dome. And just want to note, it's a highly vertical failure. You can see the sort of pyramid-shaped source area here. And the other super notable thing is just the amount of dust in the deposit area. And so you can see there's this sort of splash ring of dust on either side of the flank of the landslide. And that's also seen in this photo of the sort of toe of the deposit area. You can see a bunch of dust that's even gone over the ridge in the foreground, and some lobes of material are in the furrows of this unnamed glacier that's flowing off to the north from Peters Dome. And then in D, it's a close-up view of the source area here. You can see that the failure was obviously in rock, and that some amount of snow/ice was entrained as well. And just to highlight that this is an extremely steep failure surface. So now I want to talk a bit about the multi-event sequence that we ascertained from seismic and acoustic data. And this was work done within 24 hours. This was the following day. So when I was examining the seismic data the day after the event, I pulled data from the closest seismometer, and this is what I saw. So we have time on the x-axis, and then we have three panels. The top is showing just the frequency content of the signal, and then we have the waveform filtered in two different frequency bands. And just to note that we obviously have this very large failure occurring at around 206 with a very strong long period component, but we also have these two smaller failures occurring a few minutes before the main failure. And we see that they have similar amplitudes, they have similar shapes in the frequency domain, and there's just a little bit of a blip of long period energy associated with them. And that's for this station KTH, which is about 50 kilometers almost due north of the landslide, which I'm now showing as this green star. So I didn't know initially whether or not these were related to the main failure, because often you'll see a small shallow earthquake can have a signature that looks somewhat similar to what these look like. So I checked other stations, and I looked then at infrasound data from a station 100 kilometers away. And this is a different segment of time, but it's the same window of time. I've just shifted stuff to align, and you can see very clearly that, again, we have two arrivals prior to the main failure. And this was really important because it ruled out earthquakes as being the source of these two pre-event or pre-main failure signals. And this was an early indication that these may have also originated from the landslide, because again, this is infrasound. This is a product of a superficial source, not a source at depth. But the real smoking gun was when I examined infrasound data from the array in Fairbanks, which is over 250 kilometers away. And this is infrasound array processing. So on the top, we have the pressure waveform. The next panel is the back azimuth to the source, and here in green, the horizontal line is the back azimuth to the true location. And then the final panel is the trace velocity across the array. And this was immediately the verifier that the 4 slide signals that we saw were indeed coming from the same location as the main failure. We have 1, 2, and 3 coherent arrivals. And you might notice that there's some other signals as well, a pulse here before the second 4 slide, and then some extra energy after the main failure. And if you looked at these just with the first 2 panels, you might think that there are indeed even more events occurring. But it turns out that those are not actually new events. They're a product of what we call multipathing in the atmosphere, where sound is emitted by a source and it can take different routes to get to the array location. And so these signals here went higher into the atmosphere and traveled in a different waveguide. And then when they come back down and are incident on the array, since they're coming from higher up, they have a steeper incidence angle and they have this higher trace velocity. And so this trace velocity panel effectively helps us understand what's real source and what is acoustic multipathing. And this is just for reference, if you're not an infrasound person, this is just probably one of the coolest infrasound records I've ever seen from a mass movement. So we were curious to explore a little bit more how similar these 2 4 slide signals were to the main failure, to understand how large they were and how their durations compared. And so what we're looking at here is the time series from a station, a seismic time series, where I've highlighted the colors of these 2 4 slides on the main slide. And then the panel at right is the spectra. So it's just the energy at different frequencies for these 3 different sections of signal. And from this, you can see very clearly that those 2 4 slide signals have almost exactly the same spectral signature. And if we look at a different station that's 100 kilometers further away, we see the same picture. Albeit with a lower signal to noise ratio. And so what this tells us is that those 2 pre-event failures were about the same size. And we can also see that they were about the same duration as well. We also looked at the same type of analysis, but for infrasound. And here it's a little bit less clear, but you can still see that in terms of the energy that these 2 4 slides coupled into the atmosphere, it's quite similar. And then for the main failure, especially at lower frequencies, which is to the left in these spectra plots, there's quite a bit of energy. Although one thing that this does really highlight is how infrasound propagation is so much less clean compared to seismic wave propagation when you compare the relative amplitudes here relative to the seismic. In addition to some pre-event signals, we also observed some after slides. And so I was perusing the daily archive of Planet Labs imagery 8 days after the failure, and I was just looking to see if we saw any evidence of extra after slides. And I saw an image like this, where it's very clear that this dark patch is indicating that we still have some active rock fall coming off from the source area, which is where my laser pointer is. The failure is downhill to the north here. And there's been snow cover in the intervening days. And so this is telling us that it's still an active place. But I wasn't really prepared for the next image I saw when I clicked through to 6 minutes later and saw a plume of dust coming off of the toe of this this deposit area. And I was like, that looks very suspicious. And I was able to look at the seismic data that's corresponding to the timing of this image. And so now on the x-axis, we have time, and then we have, this is the closest station to the landslide. And sure enough, right before this image was taken, we have a seismic signal that's highly characteristic of a mass movement. And so effectively, the satellite came over and snapped a photo just as this rock fall was finishing off. And so this is the first time I've ever seen a rapid landslide that has been caught red-handed by a satellite. I thought it was a very interesting part of the story. So speaking of the geospatial side of things, now I want to talk a little bit about some of the extra data sets we brought in. And this is no longer within the 24-hour time frame. This is using additional data to understand the deposit morphology and the volume of the event. So on the left here, I'm showing a Planet Labs image that was acquired the day after the failure. And I want to just draw your attention to the dust that we saw in those photos. And I was looking at a photo like this, and I didn't have the deposit drawn on at that time, of course. And it was very difficult to identify where true deposit ended and where just a thin film of dust began. And so we quickly realized we needed a different technology that would help us delineate the deposit. And so we turned to SAR, synthetic aperture radar data, and we looked at SAR amplitude images from before and after the failure and computed the log ratio, which is basically just like a difference change detection strategy. And that's what this image is showing. And so the assumption here is SAR is sending an active signal down to the ground, and when that surface gets rougher, there'll be more backscatter back to the sensor, and so the image will appear brighter. And that's where we have this teal color. And then anywhere where the surface has gotten smoother, we'll have a reduction in brightness, which is this brown color. And since the wavelength of the SAR satellite is about 5.5 centimeters, it is sensitive to sort of the deposit material, but the thin film of dust is relatively transparent. And you can see immediately, this is actually how we delineated the deposit area of the landslide is from this this difference image, because it's very clear where the real rough deposit is located. And you can see, for example, this is a material in that furrow of the glacier. We also see some interesting effects here in the source region where it appears that things have gotten significantly darker. And we don't know if this is due to the surface being smoothed by the removal of material, or another factor, because the radar signal is also sensitive to the type of material. So maybe it's the fact that we replaced snow and ice with bare rock. In addition to this, we were also interested in estimating the volume of the landslide as another basic characterization. And for this, we performed DEM differencing, and we had a DEM from Arctic DEM acquired in 2020, but of course we had no post-event DEM, so we created one from a world view stereo pair that was acquired a month and a half after the failure. And you can see here the results of the DEM differencing. It's obvious, first of all, where the source region is, this depleted area, and then we have down at the toe here evidence of the infill of that furrow and the extent of the deposit. I will note that this lobe here, it's tempting to attribute this to some part of the deposit, but this is in fact related to a surge in the glacier that occurred sometime between 2020 and our DEM. So we have to be pretty cognizant of the large temporal baseline we're working with here. We also had this very unfortunately located hole in our post-event DEM. This is due to the extreme challenges of using stereo pairs to generate a DEM in Alaska in September, when things are overly shadowed in extremely steep north-facing topography. So don't recommend it, but we had to patch this hole. We used a parabolic fit, which I won't get into too much, but we have an estimate of about 6 million cubic meters for the source area of this event. And now's a good time to kind of help us understand the sense of scale here. So very often I'm in GIS software and I'm playing around with these polygons and don't really have a good sense of really how big anything is. So if we were to take the crown of the landslide and place it at the School of Mines M, for those of you who are Golden residents, and then it failed downslope, it would fail all the way past the Coors Brewery, past downtown Golden. So this is just one way to really understand the scale of this event. So armed with additional information about the volume and about the deposit morphology, we wanted to understand the dynamics of the failure. We wanted to reconstruct what happened. And we had two tools at our disposal to do this. One of them I've already mentioned. It's the seismic force inversion. This uses a code called Ellis force that we've developed, and we use long period seismic waveforms to invert for the time series of forces that the landslide exerts on the Earth. And this is the center of mass of the landslide. But given we had a DEM and an estimate of the source volume and geometry, we also performed numerical granular flow modeling. And this is using the model ShallTop, which is a depth-averaged thin layer approximation to granular flow. And ShallTop has a number of rheological parameters, and we did an interesting approach where we tuned the parameters of the model, which we don't necessarily know a priori. We tuned them to match our observations from data. So we are able to get the center of mass force time series from this model as well as from our force inversion. And so we were able to optimize our parameters to match what we observe from the force time series from the force inversion. In addition, we have a measure of the deposit. And so another constraint we put on our parameter optimization was ensuring that the final time step deposit of the numerical model is approximately the same as the observed deposit from satellite imagery. And so this is not a formal inversion by any means, but we're basically performing a large number of numerical simulations with different parameters in a grid search sort of fashion with a misfit function that is defined by fit to the time series of forces and fit to the deposit. Here is a sort of summary slide animation of the dynamics for the 2023 Denali avalanche. So on the left here, we have time from the start of the simulation, and we're showing the time series of forces. It's a three-dimensional force vector. So this is force exerted on the Earth in downward, northward, and eastward directions. And the solid line is the seismic force inversion. This is what we have from recorded data. And the dashed line is the output from the numerical simulation. Both of these are center of mass forces, and the numerical simulation has been filtered in the same way the seismic force inversion has. And then on the right is the movie of the failure with the vertical thickness as the color scale. And I'll note these two black lines are the trajectories of the center of mass for, again, in solid, the force inversion, and in dash, the numerical simulation. So the goal, I should back up and say the goal of running this numerical simulation was really to help us understand and interpret aspects of the force time series and really get a better handle on the dynamics. And we really were able to do that here. We see really good agreement between these two force time series. And in particular, I want to draw your attention to these downward forces occurring at 20 seconds and at 30 seconds. And these are accompanied by equal magnitude eastward forces on the Earth at 20 and 30. And if we look at our simulation here, at 20 seconds, we see that we have done this extremely vertical drop, and we've deflected off of this ridge, this first ridge here. And at 30 seconds, the same thing occurs for the second ridge. And for each of these, it's a downward force on the Earth, and then the landslide is being deflected to the west, and that means it's imparting force to the east on the Earth. So if we look at this just in a static sense to really drive it home, you can see at 20 seconds, our material is just impacting that first ridge, and it's failed down to the steep cirque, the base of the steep cirque there, and that's at 20 seconds. And then at 40 seconds, you can see the material has just come around that second ridge. And so using this combination of the force inversion from seismic data and this numerical simulation, we're effectively able to really get a reconstruction, a movie of how this landslide failed that we have a lot of confidence in because it's reinforced by the seismic data. So at this point, I'd like to wrap things up with a couple conclusions and sort of thoughts about seismic and infrasound for monitoring and response that are really taken from our experience with responding to this event and characterizing it. So the first is that seismic and infrasound really are the only way to get high temporal resolution data acquired during failure for these large and remote events. And we were able to use these data to say exactly when two force slides happened prior to the main failure. We were able to identify an after slide happening 8 days later. We're able to say precisely how long the avalanche occurred for and how it interacted with the solid Earth. From a monitoring perspective, these technologies do not require prior knowledge of failure locations. So once you install, say, an infrasound array or a seismic network, you can have landslides happening anywhere, which of course is very important because in the volcano monitoring world, you usually, not always, but you usually know where you need to set up your monitoring instrumentation. But for landslides, that's far less true in a lot of circumstances. And you might think of Barry Arm as one example where we did install infrasound directly across from the active failure. And of course, in that case, we knew where things might fail, and so we put the array there on purpose. But I think it's a great example of how infrasound can see everywhere, that the Barry Arm infrasound array itself was one of the arrays that detected this event happening hundreds of kilometers away. The existing instrumentation can be leveraged. So almost all, if not all, of the seismic and acoustic data that we used for this analysis was part of networks that were deployed for a number of things. I suppose the Barry Arm infrasound array is one that was really expressly put in for landslide monitoring. But these other arrays, the infrasound array in Fairbanks is used to monitor for atmospheric nuclear tests. And all of the seismometers we're using are really a part of a core backbone of earthquake monitoring. This event showed us that some landslides are automatically located by earthquake systems. And this is a really exciting avenue to really think about because on one hand, we can examine what aspects of this landslide contributed to it being detected by these operational systems, but we can also go back in, kind of open up the box of how these earthquake systems work to understand how they might be further modified to detect more landslides. Infrasound arrays can be used to triangulate the positions of surface events. So we had 4 arrays that captured this event. And then I will point out that imagery and on the boots on the ground recon are obviously still critical for detailed event reconstructions. I hope that parts of this talk made that absolutely clear. But I think that including these high temporal rate data streams in those reconstructions really can add to the benefits. And with that, here are my references, and then I'll just leave it on my takeaway slide, and I'm happy to answer questions. Thanks for your attention.